Hi, this is Mark Weitzman. Welcome back to my YouTube channel, Theoretical Physics with Mark Weitzman. Today I want to continue the quantum field theory student's perspective course by doing version 2 of lesson 9, which is the path integral for interacting field theory. So this is lesson 9, the path integral for interacting field theory. And this will be the first of probably three videos. This is part 1. And we start with a what we call phi cube theory. Our interacting Lagrangian will be, and I'll explain this a little bit more detail in a second. And this is the interacting term here, phi cubed. And just want to correct my notes for a second. So what Shadecki does in starting with this theory is he's sort of preparing the renormalization that will have to be made. He's sort of doing it early, and so he's putting in what constants, extra constants. Like this would normally be the free field theory, but you wouldn't have the z phi or the zm. But he's getting ready for the fact that we're going to need some renormalization. This would be the interaction term, and again, we're going to need a renormalization term. And if you recall lecture 5 with the LSC reduction formalism, when you start with like a free theory and you sometimes have to shift in order to satisfy that the vacuum expectation value is 0, and I'll get to this in a moment in more detail, and you have to shift sometimes multiplicatively to get the one particle state overlap with the vacuum to be a certain value, then you're going to automatically get a linear term, the y phi. And so what we have is we have 4, call them renormalization constants to satisfy 4 conditions. So let me just clarify that. We have physical parameters. So we have, for instance, the mass m and the coupling constant g. And m is determined by the mass of the particle, however you measure it. And like often it's just the, we can also think of it as the energy of the first excited state. Relative to the vacuum or ground state. And then we have the coupling constant g, and this is fixed by some measured experimental cross section, usually. So that, for instance, in QED, we would have the low energy Compton scattering, which is cross section, and it's proportional to e to the fourth. So that will sort of like give you the coupling constant. Remember, it's going to be like alpha is equal to e squared over 4 pi or something like that. To get the e squared, you'll just look at the low energy Compton scattering. Now, the renormalization parameters, as we've already said, we have z phi, zm, zg, and y. Now, if you studied an old quantum field theory book, not really old, but if you study a quantum field theory book that focuses on quantum electrodynamics, you'll have like the Z1, Z1, Z2, and Z3, and one of these is like wave function renormalization, one of them is charge renormalization, and one of them relates to the mass renormalization, and you get some ward identities and some interesting things which help. But right now we're just doing it in general for a scalar theory, and so we have these 4 coupling constants. And the idea is to use these constants to satisfy the physical conditions. So we have our conditions. I've already named 2 above with the mass and the coupling constant. In addition, the LSZ reduction formalism requires that the following conditions be satisfied. And the first one would be like the vacuum field, vacuum is equal to 0. So this is this sort of enforces no overlap between the vacuum and the single particle state. And then our second condition, let's call the mass condition as 1 and the coupling constant is 2. This is the third condition. Now we have the fourth condition. The fourth condition is that the matrix element between a 1 particle state, the field operator, and the vacuum is equal to e to the minus I kx. And this is what, K is a single particle state. With a relativistic normalization, like K prime K is equal to 2 pi cubed del K minus K prime 2K0. I think I got that right. Hopefully I did. So this enforces the condition that the creation operator, when it acts on the vacuum, creates a correctly normalized 1 particle state. So essentially it's Okay, so and just to write down, if we were to go to the Hamiltonian formalism, we would define our canonical momentum by the partial derivative of the Lagrangian with respect to the time derivative of the field. And it's very easy, and then minus the Lagrangian, we would get this. Pi is the canonical momentum. And this term, this is the interacting term, and this is the problem, because it's not just the negative sign there. It's the fact that it's phi cubed, because classically phi cubed, whether it will be either positive or negative, but it's not bounded below. So this is a problem. And essentially, the field can like tunnel through. You get some kind of the total of the phi squared and the phi cubed. Might look something like this. And if you're in here, you can tunnel through this space and then roll down to to a minus infinity. So it's not good for as a quantum field theory, but we're only using it to learn QFT perturbation theory. Now, most books, most other books, very few books use this theory. Most other books will look at a phi-4 theory. And you might ask, why aren't we using phi-4 theory here? Well, the pedagogy that Shigneki is using is that there are certain things in phi-4 theory that only come into play in second order in perturbation theory, and you have to like do some long calculations. And these things show up in first order in they show up in first order in phi cube theory. So that's why he's using phi cube theory. It's a little bit easier to teach and present, and yes, it's not realistic. And eventually, the only phi-4 theory that the only scalars that we know of now are the Higgs boson. So that's where we would apply a phi-4 theory anyway. Okay, so let's get to the path integral. So we have Zj defined to be the vacuum to vacuum transition amplitude in the presence of a source J. And this is equal to the integral of capital D. Remember, D is the funny measure. It hides everything we don't mathematically understand about the path integral, or so we just sweep it in under the D, but we use a capital D to remind us of that. And here we have L0 plus L1 plus J phi. So this is the interacting path integral, and what we're doing is this is our source term, our source or forcing term. This is the free Lagrangian. And everything else is basically in here. This is the interaction Lagrangian. Now, the And I'll give more detail on these terms for our specific theory in a moment, but what we do is we rewrite this with using a very nice formula. And this axon, so I didn't leave myself much room. So this is acting on, and I'm going to use a y here instead of x. It obviously doesn't matter, but the point is this x and this y are independent of each other. They're not the same variable. L0 plus J phi. So this is a master formula for doing perturbation theory through the path integral. And when I first saw this, it was very confusing to me. I think I first saw it in Ramon's book, Field Theory of Modern Primer, when I was at Caltech in like 1984. And it was new to me, and I was confused by it. But you just have to stare at it for a while and think a little bit, and it will come out. Or you can just sort of work it out. So if we expand this, if you want to understand it a little bit, expand this part in Taylor series. So what we get is 1 plus I, the integral d4x, L1, 1 over I, del j of x, plus higher order terms. So this whole thing is now acting again on this interacting field free field part. This is the free field. Now you bring this inside, when you, the one term obviously doesn't do anything, but the next term, it has functional derivatives. This is like L1 could be phi cubed in our theory. It could be phi eighth in another theory. It could be a whole polynomial. But again, you expand L1 so you get a polynomial in these functional derivatives. Well, we don't have to see exactly what they are, but when we apply this functional derivative to the path integral, we bring it inside the integral sign. We have d phi, and we have the first term, which is like 1 plus the integral d4x, I integral d4x. Now, what does this do? Well, just take one part of it. Forget about the fact that it may be raised to a certain power or something. Just take one part of it. When we take the derivative of an exponential, we get the exponential back, and then we take the derivative of the what's being exponentiated, this I d4y term. When we take a functional derivative of this, let's just imagine like right here, del jx, or 1 over I, del jx of I, the integral d4y, L0 plus j phi. Well, L0 doesn't have any j's, so we ignore that. And we take the functional derivative of j phi with respect to jx. Remember here we have the arguments are j of y, phi of y. So we take del jx of j of y, which is a delta function, del x minus y. The 1 over I here cancels the I there. And then we have del x minus y times phi of y. So this is equal to like the integral d4y del x minus y times phi of y. And then this is just equal to phi of x. So every time we apply one of these 1 over I del jx, it just brings down a phi x. So if we have a whole polynomial of them, we're going to get the whole polynomial of the phi x. So we end up getting just L, sorry, we end up just getting L1 phi, and so that's one term of it, plus the higher order terms times the e to the I, the integral d4y L0 plus j phi. So now when this thing is just the Taylor series for the exponential, so we get the integral of d phi. We're going to get the integral of, I'm sorry, we're going to get e to the I integral d4x of L1 phi times e to the I integral d4y L0 plus j phi. And we can combine these. Remember, these are not operators. When we do the path integral, the things in the path integrals are classical or Grassmann or whatever fields, but they're not operators. They're just regular, numbers. So this is equal to the integral of d phi e to the I, the integral d4y. Now you have L0 plus L1 plus j phi, and that's what we claimed earlier. So that explains that very important master formula. Now, going back, I wanted to note that before we divided our theory, L0 is the free field part, 1/2 partial mu phi partial mu phi minus 1/2 phi squared m squared phi squared. So this is the free Lagrangian. L1 is the interaction, and we sort of divide it between 1/6 ZG G phi cubed, that's the interaction term, plus something we call the counter term Lagrangian. And so this is the interaction plus counter term. So remember that the Lagrangian that we originally had, that we started the lecture on, was, it had these z's in them and the y's. When I took the free out, there were no z's and y's in this free Lagrangian, so they're going to have to appear in this counter term Lagrangian. So L counter term, and you can see this just by adding it up, how you get this, but 1/2 z phi minus 1 partial mu phi minus 1/2 zm minus 1 m squared phi squared plus y phi. So this is in a sense a renormalization counter term. If you add all these up, you'll get the Lagrangian that we started with. But we've isolated these parts from the free things because we know how to handle the free Lagrangian. That was the previous couple of lessons. We know how to handle the free Lagrangian. We don't know necessarily how to handle the interaction Lagrangian or these counter term Lagrangians, but that's what we're going to learn this lesson. Now we expect as the coupling constant goes to 0, we get a free theory. So we expect that y goes to 0 and the 3z's go to 1. Actually, we'll find that y is order of order g, so it's like linear in g, and the z's are 1 plus order g squared. We expect to find that, and we'll compute it, and we'll see that that holds. Now, L0, just using L0, we know that we get Z0J, and we had already evaluated Z0J before. I forgot to write it. We've already evaluated d phi e to the I integral d4y L0 plus j phi. This is equal to e to the I over 2, the integral d4x prime. And we have a source, then we have the Feynman propagate, and the source again. So we already know this. But the main thing is, at the end of the day, we're going to want to show that we're going to want to enforce the condition. This is another thing we need to enforce, the overall normalization condition, that Z0 equals 1. So we're going to start out by ignoring the counter terms. We'll treat those later. And we have we'll call it Z1J because we're ignoring the counter terms, so it's not quite our complete interaction thing. And this is going to be exponential I over 6 ZGG integral of d4x 1 over I del x cubed acting on Z0J. So what we've done is we've gone back, as I said, I've just ignored this term right now. We'll take care of them later. And we'll just use our interaction term, the phi cube theory, to start our expansion. And we'll again fix Z1J, Z10 equal to 1 at the end of the day. Now that's what the proportionality constant is there before. So we get this real nice, put 2 stars, double Taylor expansion. Sum from v equals 0 to infinity, 1 over v factorial. So we're going to expand the first term, and then we're going to expand acting on the second term. I ZGG over 6 integral d4x 1 over I del jx cubed and this is to v because this is what we're expanding in here, so it Taylor series 1 over v factorial to the exponent v. And then we have our Z0J, which we can also expand right over here, this specific term. Let's also expand that in a Taylor series or power series, whatever you want to call it. So the sum from P equals 0 to infinity. 1 over p factorial I over 2 integral d4y, I'm sorry, alright, d4y, d4z, jy, Feynman propagator, jz, and this to the exponent p. Now I chose the letters v and p for my Taylor series expansion. This is a double Taylor series expansion.
It doesn't look like you have an app named Expansion. You can search for it in the App Store.
It's unbelievable. Sorry about that. Double Taylor series expansion. You don't really see it in too many books explicitly. It's there implicitly, but one of the things I like about Czarnecki's book is that he shows this explicitly. Let me just define some terms. E we haven't really used yet, but we'll relate it to P and V. So these are our external sources. V will be our vertices. And P will be our propagators. And you can see that E will be equal to 2P minus 3V for a particular V comma P term in the series. So let's see how that works. If we go back here, if we have P propagators, for each propagator we have two sources, so we're going to have 2P sources. And now each vertex has three functional derivatives, which each functional derivative gets rid of source. So we have 2P minus 3V. So this will tell us how many sources we have left, basically, external sources. Now, the phase factor, the overall phase factor, this is I to the V, because we have this term here, this I, so that's going to have I to the V. We're going to have 1 over I to the 3V, because we have this term in the denominator, and then it's raised to the power 3 and raised to the power V. So that's 1 over I to the 3V. And then we have I to the P, because in the propagator term, this I will get raised to the power of P. And this is equal to, using this relationship, you can easily verify that it's V plus E minus P. And also you might notice we have 3V functional derivatives for a particular term. They act on 2P sources in 2P factorial over 2P minus 3V factorial ways, or different combinations. So we'll talk about more of that when we get to symmetry factors in a moment. So the way to organize this Taylor series, and the genius of Feynman was he was the first to do this, among many other things, but it's hard to work just with the mathematical terms, but it's much easier if you go to diagrams. So we use Feynman diagrams. And we have a dictionary, sort of like translate. So something like a line between 2 points, x comma y, this is represented by the mathematical term 1 over I del x minus y. So this is just the Feynman propagator. And we're going to represent the sources by a filled dot with a line attached to it. The x, I mean, you can think of the x as being right next to it or right over here, but there's no propagation between the source and x. The source is at x. And we represent this mathematically. Actually, we're representing the mathematical terms by these diagrams. I, the integral of d4x jx, so that's a source. And then when we have a vertex, this is not a source, this is just a vertex. We're going to, this is what we use to represent I dg, the integral of d4x. Again, x is the dot where the 3 lines intersect. So we have 3 intersecting lines because we have phi cubed theory. If we had 5 to the 4th theory, we would have 4 intersecting lines. That's where it comes from. And this is the vertex. Now, let's do some naive counting of terms that we get in the Taylor series. So the idea is that in the Taylor series, as you can see going back to it, there's all these factors, like there's a 6, a v factorial, p factorial, and a 2. I got the phase already, but I'm not too worried about the phase right now. But it's, do we want to have to keep track of all these factors for each diagram? And we'll see that the way it's set up right now, we don't have to. Because for a particular diagram, with p lines or propagators and v vertices. By the way, p and v doesn't fix the diagram. There could be different diagrams with p and v. We're talking about the same diagram, topologically the same diagram. So you should keep that in mind. But we can rearrange, we can do various, when we evaluate the terms, we can rearrange the 3 functional derivatives at each vertex. So that will give us 3 factorial, a factor of 3 factorial. We can rearrange the vertices in the diagram, sort of switch 2 vertices or n vertices. That would give us v factorial possibilities. Then we can rearrange 2 sources at each propagator. That gives us 2 factorial. And then we can rearrange all the propagators. That gives us p factorial. And so the idea is we're going to get 2 factorial. We expect to get the number of possible diagrams we might get that are all the same diagram out of the expansion. We might get 2 factorial times 3 factorial times v factorial times p factorial. This is a naive, no symmetry situation. Now this exactly cancels all of the factors in our double Taylor series expansion. Cancels the 2 there, the p factorial, 3 factorial is 6, and the v factorial. So with this, there would be sort of like a one-to-one correspondence between a diagram and a term in the double Taylor series expansion. But this is naive. It doesn't turn out that way. So this, let me just write it down, cancels all the numerical factors in the double Taylor series. I think I'm going to have another lawsuit against Apple with Siri's listening in. So, unfortunately, we are overcounting. So it's sort of like when you have a Venn diagram. Let's say you have 2 circles. If you want to get the area, you can't just add the area of the first circle, let's call this C1 and C2, and that plus the area of the second circle, because you're overcounting with a overlap. It's the same thing here. We have an overlap of symmetries. Where doing one symmetry is equivalent to doing the other symmetry as well, and you only get to do them once. So what we need to do is we need to take this into account, and that we define what we call a symmetry factor. A symmetry factor, where when we have some kind of diagram, some kind of, let's say we have a diagram like this, and we would write down our mathematical expression. We would go like, we'd use our dictionary, and so we'd have like a very complicated, we'd have I, the integral d4x, jx, let's say this is x, this is y, and this is z, and then we would have, I need this too, w, then we would have a propagator, 1 over I del x minus w, and then we would have other propagators, and then we would have these vertices. So I don't want to write down the whole expression, but you can see it's a fairly complicated expression. But when we get the whole thing, this doesn't correspond to a term in the double Taylor series because it's too much. We have to divide by a symmetry factor, just a numerical factor. For this diagram, it happens to be equal to 2 squared equal to 4 is what the symmetry factor is. So the actual thing we have to calculate is 1/4 of that. If we actually, well, I'll get to that in a second. But so this is what the symmetry factor is, and Czernicki gives arguments for how to get this symmetry factor, and he has it on all the diagrams in his book. He has the figures with the symmetry factors below the book. Now, he uses some arguments, and I'll give one in a second, but they're not that obvious to me, and you sort of have to be really good at combinatorics, especially for a complicated diagram. But as a practical matter, at least for students, usually we hardly ever calculate diagram with a symmetry factor greater than 2. So this is not the most important thing to worry about, these symmetry factors. Also, you can always go back to the double Taylor expansion and just actually work it out. It's very tedious to do by hand, but you could do it mathematically, using software and verify what these symmetry factors are. The purpose of the symmetry factors is to be able to look at a diagram and do some symmetry reasoning and combinatorial reasoning, so you don't have to go through that whole calculation. But I have a video, I have a deep dive video where I do this for a very, very simple S equal 2 diagram. This diagram, I chose like the simplest one I could find, S equal 2. And I actually do the double Taylor series expansion and show that S equals 2. So I suggest watching that video after you've watched these review videos on the lesson, and you'll see sort of how to do it without any reasoning, just by brute force calculation. So let's just take one diagram that Sernecki does 3. I'll do the first one that he does. I'll do it like he does it. But basically he says that the 3 factorial ways to arrange the 3 propagators are duplicated by exchanging the derivatives at the vertices. So we could exchange this propagator with this propagator. That's one thing we could do. Or we could just exchange a functional derivative at this vertex with another functional derivative for the one that we use below. So before, when we said we had like 6 for the at each vertex, we can use those to do the propagators here. And the also, when we did the symmetry, the endpoints of each propagator swap, we always have that symmetry, 2 factorial ways. That also can be duplicated by swapping the vertices. So when I did that naive counting, as you recall, I said we can rearrange the vertices and we can rearrange the propagators. Well, some of these we're doing the same thing, so we're over counting and canceling our factors there. And so we have less of these to cancel. That's the idea. Okay. So thus S is equal to 2 times 3 factorial, which is equal to 12. And using this type of reasoning, you can get all the symmetry factors. So I want to continue with this lesson. The next video we'll start talking about connected and disconnected diagrams and how to handle all of those. So I'll see you next time. Thank you very much. Bye bye.